Hey guys, welcome to this beginning intro to our chapter on acids and bases and the equilibria associated there with that. Check out this cute artwork. I've got a bottle of milk of magnesia which has a basic component to it, which is dissolving the acid. Some folks take this when they have a heartburn, which is in some cases an excess of stomach acid. Also kind of cute, isn't it? This is the shape of the stomach. The esophagus. Anyways, did you know that acids and bases neutralize each other? That's what we say. Sometimes it's not exactly neutral at a pH of 7, if you've even heard of the word pH. But anyways, in this video, let's look at some definitions of acids and bases, some examples of acids and bases and conjugate pairs, maybe even get into something of strengths of acids and bases a little bit, and go from there. Let's look at some definitions. One of our first definitions, and maybe the simplest, is that of the Arrhenius definition of acids and bases. This needs to be in water, or we simplify and say in water an acid is this and a base is this, so aqueous solutions. And this is the dude that first gave us the idea of ions in the first place being created when something dissolves in water. And he said that an acid is anything that produces hydrogen ion in the water, and a base is anything that produces hydroxide ion in the water. Interesting. We'll see a bunch of examples of that. And then again, that's the most common and the simplest definition. Another definition, the Bronsted-Lowry definition, focuses on protons. Proton donor, proton acceptor. But basically the proton is the hydrogen ion. I'll say more about that in just a second. So in a way, this is a twisted version of this, but it perhaps could pertain or apply in other situations where the first wouldn't. And the last definition, which we'll get to more toward the end of the chapter, but also very important in organic chemistry, the Lewis definition. Gilbert Lewis focus on electron pairs. So isn't the proton the opposite of the electron? So if I'm a proton donor, I'm also an electron pair acceptor. Or if I'm a proton acceptor, I'm an electron pair donor. And the word pair isn't even necessary there, but usually electrons come in pairs, and so some things will accept electron pairs, some things will donate electron pairs, some negativity here or some positivity here. So what's up with this proton? What's up with this hydrogen ion? Well, of course, a hydrogen atom just has one proton and one electron and then one s orbital, but that electron's pretty easy to remove, actually, so it can be attracted by anything with a little bit more vigor than this is attracting, and I get what some folks call a naked proton just floating around. But it never really occurs just lonely like that. It always attracts some negativity or lone pair on something else. So the proton, especially in the water, is attracted to other water molecules. Here's one thing that's kind of amazing that water does, but it just automatically dissociates a little bit. Here's a water molecule, I got a bond there, I got a bond there. For some reason, every now and then this bond decides to break. And when that bond breaks, the hydrogen leaves its electron behind to the oxygen, creating the hydroxide ion. Also, the hydrogen plus, H plus, floating around in the water? Not really, because the positive is strongly attracted to other negatives. Here's another way to write it, which definitely is the better, more complete description. Water molecule hits another water molecule. This negativity is attracted to that positivity, and the hydrogen transfers over onto that oxygen, creating what we call the hydronium ion. So really there are no naked protons, just like hydrogen ions by themselves aqueous. They're all hooked up with at least one other water and perhaps surrounded by others. And there's the hydroxide. So interesting that water can do this, creating a little bit of acid-based nature to the solution, even in pure water. So anyways, notice the equilibrium arrows as well, back and forth. But you know what? Let's see. The degree to which this happens in normal pure water, 0.000001 moles in a liter. So not very much, eh? We'll talk more about that number in a future slide, I'm sure. Here's another proton transfer where I have HCl, perhaps hydrogen chloride gas, dissolving in water. The hydrogen is strongly attracted to the electronegativity probably out of a million, maybe one doesn't come off the chloride. But but in any case, this is what happens. It's called a strong acid. HCl is a strong acid because the equilibrium lies far to the right, so far to the right that this constant would be in the millions. It's almost not even worth saying that it's an equilibrium. You can just erase that little backwards arrow. Here's another one. This acid's not as strong, even though it's in the same family, fluorine and chlorine. This acid does transfer protein to water, but the degree to which this happens is not in the millions. Not out of a million, let me say out of 100 HF hydrogen fluoride molecules, how many of them would transfer their hydrogen over onto the water? Maybe 7 out of 100. So that's a little bit of a confusing idea, but so I still have a whole bunch more of this HF molecule staying together in the water, but still a little bit of this. But again, the equal part is the coming and the going, the forward and the backward. We write HF aqueous equilibrium with H plus and F minus, and the constant for this, like I said, is maybe about 7 of these come apart out of 100. Here's another proton transfer, water, and this is vinegar. So here's the vinegar molecule. This is the acidic hydrogen on this carboxylic acid group. This is a very, very common acid group in organic chemistry, and this hydrogen transfers over onto the oxygen. You could call it, again, just an H plus ion in water, but we know that it's H3O plus at least. And then what's left over is this little bond is cleaved, but that oxygen retains the lone pair, and so this whole ion, the acetate ion, there's lots of different ways to write that. Vinegar is the most common, most famous weak acid in the world. Another weak acid. Weak acids have equilibria, but the strong acids just go pretty much forward one way. What is this? This is benzoic acid. This is the benzene ring, the carboxylic acid group that we saw before. Same story. Hydrogen transfers over onto the oxygen. But actually, this thing makes a difference. This thing, whatever is attached to this carbon, helps determine how strong of an acid these structures are. Many different ways to write that. I like the structural thing all drawn out so I can kind of see what's transferring where. The general symbolism, the way we always write these acid-base equilibria look like this. HA is the weak acid, it's in water, and some of those hydrogens from the HA transfer over onto the water. The simplified version is HA in equilibrium with H plus and A minus. And so I could write this equation because pure liquids aren't involved in the equilibrium constant expression, or I could write this one. So the difference between this one and this one is that H3O plus versus the H plus, but we know that H plus in water is really H3O plus. But like the rules of writing these constants, these go in the upstairs and this goes in the downstairs. So if I only knew how much of this compared to how much of my starting concentration original, wrong. If I only knew how much of these are created as compared to what's left of the original acid in the water, then I know my constant. And the smaller the constant, the weaker the acid, and the bigger the constant, the stronger the acid. So the strong acids like hydrochloric and nitric and sulfuric have constants in the millions and millions. It's not even worth saying it's an equilibrium. Hey, let's look at some equations and reactions. Always in this transfer of protons from one to another, there's a thing that gives up the hydrogen, it's called the acid, and the thing that gains the hydrogen ion is called the base. So let me call water the acid here because I see the water gives up a hydrogen to the NH3, creating NH4+. So we're adding an H plus from the water over to the ammonia, and the OH is left over. Sometimes I write water HOH to show that one of the hydrogens goes over there, and the other OH is still left behind. Let me call this the acid. It becomes the conjugate base, and the base becomes the conjugate acid. So the only difference between an acid and its conjugate base pair, or the base and its conjugate acid, is one hydrogen ion, in other words, the H plus. So if I write the equilibrium constant for this, I could call it a Kb, a base, since this is a base in water, creating the hydroxide. Alright, these two in the upstairs, that goes in the downstairs, but pure liquids aren't written in the constant expression, so there you go. This is kind of a new idea. It's a new application of an old idea from the last chapter, but it'll take a lot of practice on our part to get to the place where we can write that out easily, quickly, and we can know it well. OCl minus ion, any negativity in the water, it turns out, is highly attracted, or can be highly attracted to the H plus of a water. The hydrogen atom ion of a water molecule. And indeed, this OCl minus base attracts one of those, creating that. I don't know what the constant for this is. Again, I called it a Kb for this base attracting that hydrogen off there. But anyways, the base becomes a conjugate acid. There's the acid part of it. And the acid becomes a conjugate base. I pair them up like that. Leave out the water out of the constant equation. Let's see. So here water was an acid, but you know what? In many different situations, water can act like a base. So let's try this one. Here my HSO4 hydrogen sulfate or bisulfate ion is interacting with the water a little bit, equilibrium. And I say, I'll call this the base because now it gives up its, it takes on a hydrogen from the bisulfate, from the hydrogen sulfate. So this H floats over onto this water, creating the H3O+. I called this the acid because it lost the hydrogen to become the conjugate base. I called this the base because it gained a hydrogen to become the conjugate acid. Interesting. Am I speaking too quickly here? I don't know. You can slow me down, pause me, rewind me. Another example of a negative ion in the water. This H2O. This one could go either way depending on what it's in. But if it's in water, this negativity may be attracted to the positivity there. So I call this the base. It becomes the conjugate acid. And I call this the acid because it becomes a conjugate base. We're talking about just adding or subtracting a hydrogen ion in each case. And if you gain a hydrogen, you're a base. If you lose a hydrogen ion, you're an acid. Another example. Too many examples. Can you ever have too many examples? Yeah, you probably can. Like, there's no way you can memorize all this. I don't mean to laugh at what all this information I'm throwing your way. I'm just saying there's no possible way that you can memorize this, but you look for patterns. So let's look at this thing. Did it lose or gain a hydrogen, this HNO2 thing? Well, you already know the answer. It's right there, but I'll look across here. I see the HNO2 became the NO2 minus, so this is the acid losing its hydrogen ion, becoming the conjugate base. Call water the base in this case, creating the conjugate acid by gaining the hydrogen ion. Oh, I simplified here. Instead of H3O+, here it's H+. Hey, before we stop, let me point this out. And if you haven't already thought about this, you should think about this soon. What are the strong acids? One reason why it's good to know the strong acids is there's only a certain number of them, but there are hundreds and hundreds of weak acids. But if you know what the strong acids are and how they dissociate, what they're called, and how they come apart in the water, I know that 100% of the HCl comes apart, and the H-hydriodic acid, hydrobromic acid, nitric acid, they all come apart totally. So if you know what the strong acids are, then if you see a weak acid with H in front, you go, aha, that's weak, and then you know there's an you're doomed for an equilibrium. And likewise, the strong bases. One good reason to know the strong bases, because there are hundreds of weak bases. I also know that most hydroxides don't dissolve in water, but I do know the strong bases do dissolve in water. So in any case, sodium, lithium, potassium, rubidium, cesium, all in the first family of the hydroxides. Those salts dissolve in the water really well. These not so well, calcium not so well, but it still breaks apart 100% of what of it does dissolve in the water. So anyways, know your strong acids and strong bases. These are named as hydroxides: sodium hydroxide, lithium hydroxide, potassium, calcium hydroxide, strontium hydroxide, barium hydroxide. Ooh, I ran out of time. Thanks guys for watching. I'll catch you next time. We're in lecture. Take care.